Okay, so welcome back to another video. So here today we have a Putnam Exam question from 1968. This is question A1, and we want to show that the definite integral from 0 to 1 of x to the power 4 multiplied by 1 minus x quantity to the power 4 divided by 1 plus x squared dx is equal to 22 divided by 7 minus pi. So this is actually a very special question. Well, I think it's also worth noting that this is probably one of the easier Putnam Exams questions out there, especially now I think about it from that previous limit question that I did from the 2021 exam. But the result is actually special because, for one, this is actually the way, as you can describe it, as a progenitor of saying that the result of 22 over 7 is actually strictly greater than pi. But I'll get to that extension towards the end of solving this integral, and you can see why this is actually considered very special. But for right now, let's actually show that the left-hand side is indeed equal to the right-hand side. But simply, this is actually more of a straightforward approach by using not necessarily any sort of substitution, but rather once you think of more of a, when I say direct, it's more like we can actually expand what's in the quantity, then, do a little bit of distribution with, those polynomials. And then you see that we can actually perform a little bit of some polynomial long division. Straightforward as it gets in there. And then finding the definite integral after that whole simplification will make things a little bit easier. And the result will come out nice, just like the way it's listed on the right-hand side. So let's actually just jump right in. So by expanding the left-hand side, so if I say that this is 0, 1, of x to the power 4. So suppose that, let's expand the quantity of the inside. So that means we have to do this, multiply this 4 times. To make things a little bit easier, how about I actually do twice of each? So I take this as 1 minus x to the power square multiplied by 1 minus x to the power square. So, and then performing that expansion, we'll see that we have 1 minus 2x, add this with x squared. Then we just do this again for a second time, 2x plus x squared, all this being divided by 1 plus x squared dx. Then simply we can actually do a little bit more, multiplying this together as well. So 0, 1, x to the power 4. Then we see from the quantity of the inside here, we get the following terms. We have 1 subtract 2x, add this with x squared, and you can check this yourself to see the multiplication. Then minus 2x, add this with 4x squared, minus 2x cubed, plus x squared, subtract 2x cubed, and then add this with x to the power 4. Then, still being divided by the same divisor over here, 1 plus x squared dx. Now simply, we can see that if we actually just combine all those terms together, then you'll see that the binomial, the coefficients associated with these terms is actually what you notice from, Pascal's triangle. Simply, I say that specifically we have this as 1 minus 4x, add this with 6x squared, subtract 4x cubed, and then add this with x to the power 4. You see these coefficients 1, 4, 6, 4, 1. Those are, the numbers from, you see a Pascal's triangle with the whole expansion. Now, let's see, this is still divided by the same thing, x squared dx. Then if I just do a little bit of distribution, then our integral that we have so far after performing that is x to the power 4 subtract 4x to the power 5, add this with 6x to the power 6, subtract 4x to the power 7, and then add this with x to the power 8, all divided by 1 plus x squared dx. And now, as I mentioned, we're actually going to be performing some polynomial long division over here. And we usually, with polynomial long divisions, we want to start off with the highest degree. Thankfully, all these terms are commutative, so we can actually just rearrange the terms. Same thing for your divisor. If your divisor wants to start off with the highest degree in there to make the division a little bit easier, so we can actually, luckily we can do that. So now let's actually perform this long division. So I'm going to start off, we have x squared plus 1, and then all this being divided by, now we have x8 minus 4x to the 7 plus 6x to the 6 minus 4x to the 5th, and then add this with x to the power 4. So now we just have to, find some kind of multiple so that it actually fits, the whole description once we do the subtraction. So first we can actually, multiply our divisor with x to the power 6. perform this. So we have x to the power 8th. Then, well, there's nothing for the 7, so the 7th power, so we fill this as 0 times x to the power 7. Then add this with x to the power 6. Then we actually just subtract the entire thing. Then we see that these terms are going to cancel, and then now we have a 4x to the 7, or negative 4x to the 7, then subtract 0, so this is negative 4x to the 7. Subtract this term, then we have this is plus 5x to the 6, and then we just drop in these remainder terms over here, 4x to the 5th, and then add this with x to the 4th. So now let's continue on. We can now distribute, or rather multiply with a minus 4x to the 5th. Then if I just multiply with our divisor, then we have 4x, or rather minus 4x to the 7th. Then there's nothing for the x to the power 6 term, so I'll put a 0 times x to the 6. Then distribute for the negative 4x to the 5th to 1, so minus 4x to the 5th. Then if we just perform that entire subtraction over here, let's see, so this is going to cancel, so this will be drop down to 5x to the 6 over here, multiply here, that's going to get rid of itself, and then we just drop down with the plus x to the power 4. Okay, we can still keep going. Now we see that let's actually distribute a plus 5 multiplied by x to the power 4. Then do the same thing. Then we see that we have 5x to the 6, and then luckily 5x to the 4th over here. Then let's see, the terms cancel each other out. Then x to the power 4 minus 4x to the power, or minus 5x to the power 4. We'll have minus 4 times x to the 4th. And then there's still a, we still have an x square because we can actually still keep going. So I'll actually just add a 0x square. We can still continue. This is still we can still continue dividing. So from here, now we can actually suppose we multiply a negative 4x square, and then by performing all this, so we have minus 4x square, and then distribute the 4x square over here. So this is minus 4x squared. That's actually supposed to be the degree is supposed to be 4 on this one over here. Then we just subtract everything, so this cancels, and so we have a minus 4x squared. Then we can still continue on because there's an x squared plus 1, so finally we can actually put this as plus 4 and multiply that. So 4x squared, then multiply, then plus 4. So that means all we're left with is minus 4. These cancel, but this actually leaves out to say that we have a remainder of negative 4. So therefore, our new integral over here, let's put this in a different color. Our new integral we're going to have now is the following. So after all this division, so this new simplified integral after this division from here is we're going to have x to the power 6 minus 4 times x to the power 5. Add this with 5x to the 4th. Everything's just coming from here. Subtract 4x squared plus 4, and now we have to deal with our remainder. So minus 4 and then divided by that divisor. So minus 4 divided by 1 plus x squared, then dx. Now everything here is, you can actually easily find their own antiderivative. So thankfully that's actually an amazing accomplishment from there. So after performing all the finding this antiderivative, then we actually have the following formula. So we have 1 over 7 x to the power 7, then subtract 4 divided by 6. I can simplify that out later. Let's just actually make things a little bit easier on our hand. Minus 4 divided by 6 times x to the power 6. Add this with x to the power 5, then subtract with 4 over 3 x to the power 3, then add this with 4x. And then finally, we know the antiderivative of 1 over 1 plus x squared, which is basically just the inverse tangent. So minus 4 times inverse tangent of x. And then all this, we had to evaluate our bounds from 1 to 0. Luckily, that's nice that anything you plug for 0, it's just everything's going to be 0, so that's fine. So we plug in for 1, so we have 1 over 7, then subtract, so 4 over 6, so simplify that to 2 over 3. Add this with 1, then subtract 4 over 3, then plus 4. And lastly, if we plug 1 for the inverse tangent of 1 is actually just pi over 4, then multiply to 4, so we have minus pi Then subtract 0 coming from 0 is distributing from plugging in for everything in here. So thankfully that's at least a headache that we have to deal with. Simplify all this out. We have a 66 divided by 21 minus pi after computing all this out. Well, we're just leaving pi on own. We're just dealing with these, rational numbers over here and the 1 and 4. Then we can simplify this out to say we have 22 divided by 7 subtract pi. And so therefore we have shown that the left-hand side over here is equal to the right-hand side. All right, so that actually completes the proof of this. So now we want to know, as I mentioned, why is 22 over 7 strictly greater than pi? Well, I'm not going to give too much, writing, but I'll give more of the basic explanation or simpler terms on how to see the picture here. We see that our given integrand over here, everything in the exponent has even degree and powers. So even degrees, meaning that, you're always going to get a positive number, basically saying that this entire integral itself is actually going to be strictly positive. So in its term to say this, that means I'll put this as our given integral 0, 1 of x to the power 4, 1 minus x to the power 4 divided by 1 plus x squared dx is strictly greater than 0. We just showed that this integral is equal to 22 divided by 7 minus pi is greater than 0. You just do the algebra when it comes to inequalities and see that 22 over 7 is indeed strictly greater than pi. It's actually, interestingly, 22 over 7 is actually a widely used Diophantine approximation for pi that basically says that these are approximations of real numbers by rational numbers. So there's also, interestingly, I know it's not much to explain, but the rational number 355 divided by 13 is also greater than pi. And the proof is basically in a similar of an integral format, but of course the integrand is different. I actually forgot what the integrand was, but there's another proof that says that, shows that 355 over 13 is strictly greater than pi. So yep, that's pretty cool if you ask me.